Let's get started today. We have the big item on the agenda is to start into our second design strategy or technique, which is called normalization. It's the bottom-up technique. Before we do that, I also want to go over one of the quiz problems that dealt with ER diagrams to give you an idea of how to solve it, and it might help also with the homework assignments. And I also wanted to emphasize a couple things about ER diagrams that also might help with the homework assignments. So we'll do that first. So the first thing I wanted to emphasize with ER diagrams is don't reuse relationship names. I see a lot of homework solutions. I see a lot of midterm solutions where the verb has is used multiple times. And the issue with reusing relationship names is you introduced ambiguity both into your ER diagrams and when you're discussing the relationship types with your colleagues. So it's good to use unique relationship names. Secondly, use informative relationship names. And typically relationship names are action verbs. Where the action verb describes the relationship between the two or more entities. Don't use passive verbs if you can avoid it. It is much better to say something like office employs staff rather than office has staff. Or to say that a course enrolls students rather than a course has students. Enrolls employs, they're more descriptive of the relationship than has. Has doesn't really convey what that relationship is. Okay? So those are the two big things on relationship names. Now, quiz question. It's going to illustrate a commonly recurring theme. So let me bring that quiz question up. It was question 3 where you had a company and it was offering courses. It also had instructors who taught the courses. And I asked you to identify the relationships that were involved here, which actually required that you first identify the entities that were involved. So the entities that are essentially involved here are instructors, courses, students, and then you have two things that are a little harder to figure out. One is teaching team, and you have course development. That's 2, and you have training session. So those are 3 that may be a little less clear what to do with. So I think course development on one or new courses kind of implies it's different than your actively taught courses. So I would say that is a different entity representing new courses. Then training session This comes up a lot. Training session is really one or more instances of a course, and it itself is a entity. It has often a physical presence, like this section of 465 is a physical section in this room. There is a catalog entry for 465. So 465 is a course whose existence is independent of the independent sections that are offered. There was one section that's offered this semester. Another section of 465 was offered in fall of 2016. And another was offered in fall of 2015. So a session is itself an entity. It is what we would call a weak entity. It depends on courses for its existence. But you see this kind of relationship come up fairly frequently. I believe in your homework assignment you'll have video rental company. And you will have that you have a title and then you have one or more copies of that title. That's the same situation. The title is one entity, it's part of your video catalog. And then you have copies of that title. So each copy is also an entity. Well, not each copy, but the copies are also an entity type, and each copy is an occurrence. Okay, you have that with a library. A library has, again, a catalog, which describes its books, and a book will have a title, an author, a publication date, an ISBN number. You may have multiple copies of the same book. So there again, you have two entities, one representing, in effect, your titles, and a second representing copies of books. So session and courses also has that flavor of a course in a catalog and then specific instances of it which are a session. And they're both entities. Okay, so this kind of relationship, this weak, strong entity relationship comes up very frequently. It comes up in your homework assignment. It came up in this problem. Okay, and there were some easy relationships here. So you had instructors develop new courses. You had that a training session enrolls students. Let me get rid of some of the underlining here. I know I haven't gotten to teams yet. Let me just roll on. So we have a course has training sessions, and again, I would try to get away. I know I used the word has. I would try to get away from that. I would probably, although it's hard, so a course maybe offers section. And then you really get into this issue of what is a team. And when I first started, I actually thought of a team as being a physical entity. But over time, I have gravitated to the fact that really it is a relationship. That instructors teach, or if you want, team teach courses. And an instructor can teach a maximum of 0, can be on anywhere from 0 to 2, a maximum of 2 teaching teams, and a teaching team has 2 or more instructors, so a course is taught by 2 or more instructors. So I actually have, whoops, not this one. This was right. Instructors teach courses, instructors develop courses, and courses offer sessions were the 4 correct answers here. So putting team as an entity kind of obscures the fact that there is a direct relationship between instructors and courses. I know that instructors belong to teams and teams teach courses, but ultimately instructors teach courses. And so, as I said, I've gravitated to this notion that it's really a relationship, that team is a relationship here. Also, I'm not going to quibble if you say that session is a multi-way relationship. So you actually, or actually is a relationship where a course is, a session rather, if you had it as a two-way relationship here through sessions, I wouldn't think this was horrible. And if, as is often the case in a university, different professors teach courses, it's actually rather rare for a team to always teach the same course. I would think that you might say that an instructor offers a section of a course to students. It's not letting me write over here at the edge. I'm trying to write course here, but it's not putting an arrow there. It won't let me write in there all the way. So this would, in many, I wouldn't quibble with that either, that a section is actually a relationship where an instructor teaches a course to some students. So it sometimes becomes a little bit context dependent. Here, I really think of sessions as being more of a entity, rather, because instructors teach courses and it's not really instructors teach sessions. So there, I really think the relationship is between instructors and courses. Yes?
So suppose that you did treat team as an entity. It seems like the only attributes it would have would be the foreign keys of the instructors and then a primary key for that team.
Yes.
It would have no attributes really of its own. Is that
Right.
a good rule for?
Yes, that's a good rule for why it's probably also better off as a relationship rather than as a entity, when it doesn't seem to have any attributes other than foreign keys. That's a great point. That's a great way of, if your relation ends up with only foreign keys and maybe what looks like an artificial key, that's probably a relationship. And that's a good point. Here, the only real attributes with the team would probably be foreign keys for the course, the instructor, and maybe a foreign key for the team. Yes? So run that by me again. If a team is teaching more than one class, is what you're saying? Let's see. So it's a DTD taught by a single teaching team of 2 or more instructors. So right, in this case, I guess the way I interpret it is, since each course is taught by a single teaching team, but you're right, I think your question is, if a teaching team could teach multiple courses, and then an instructor could be assigned to 2 teams, then it would certainly be the case that an instructor could teach more than 2. Yes. And pardon? Yes, you could still treat that as a relationship, although I'd have to think, off the top of my head, I'm not exactly sure how I would represent that relationship. I would need to think about, in that case, how I would want to do it. Okay? And in that case, let me think about it, okay, how I would do that. Off the top of my head, I'm not exactly sure how I do that. Okay, I'll post the answer on Piazza. Pardon? Yes, appears on the homework assignment. You're right. So let me flip over to the homework assignment for a second. And it's question 2. Okay, so in this case, here's the key phrase. I would interpret this as meaning that each course that the teaching team is unique to each course, rather than that the same teaching team may teach multiple courses, okay? So I treat this sentence just like in the quiz, that it is each teaching team teaches exactly 1 course. And even if the, quote, same teaching team teaches another course, that's coincidental, okay, is how I would do it. Yes?
So I kind of get from that an instructor is either teaching or developing a course, but not doing both. Is that correct?
Yes. Now, this is one situation where, in part, we didn't cover some more advanced material in the next chapter. And if we had, I believe there's a more elegant way with UML to denote this OR relationship, but we didn't cover that advanced material. So for our purposes, we're just going to show them as 2 separate entities with arrows going to them. But I believe in UML, there's actually an explicit way to say this is an OR relationship. We just don't have time to cover it. Other questions? Okay, so I know I erased the answer now, but one of the important points there was this notion of a title or a course having multiple instances or occurrences of it, and that both of those can be considered an entity. For those of you who are familiar with the class instance model in object-oriented programming, it's the same idea. You can have a class, and some languages like Java treat the class as an entity. And then you can also have instances of the class, and the instances are also entities. So in this case, it would be a many-to-one relationship, as long as it's single inheritance. You have a class can have 0 or more instances. An instance belongs to exactly 1 class. So it's that's the analogy to think of. Yes?
This doesn't really apply on the quiz, but in the homework, would the company be considered a separate entity?
That's a great question. So the question is, would the company be considered a entity? And the answer is no. And actually that came up on the quiz too. On the quiz it also came up with. So the reason is the database is actually about the company.
Right.
And let's say you made the company an entity, how many tuples would be in the relation for that entity? 1. just the one tuple representing the company. So it's not actually you often see this in a problem, the company, the firm, the university. Those aren't considered entities. They're considered the database. Okay, yes.
So I guess the follow-up to that is, it says the company offers 5 advanced technology courses. That 5 is kind of meaningless for our purposes, because where would you represent that?
It is kind of, I don't think actually in this case you can represent that.
So it could just easily be a number of.
Yes.
Okay.
Yep. That now in the database you could have a constraint presumably that says count star must be less than or equal to 5 if you're going to limit it like that.
And the same would be true of the number of instructors?
Yes.
Okay. That's what threw me off. I had 2
Yep.
different branches off of it.
I think the book there was, but yeah, now the 100 trainees per training session is different.
Right.
But yes, the company is not an entity, and certainly I can see where that would throw you off. 30 instructors and 5. I mean, one place you could use the 30 instructors is it does actually place a limit on your teaching team, but that's kind of, I mean, really, are we limiting ourselves to 30 or 5? Probably not. So that was probably bad of the book to even say that. I agree. I think it confuses the question. Other questions about the homework or the quiz? Okay. So that finishes off ER diagrams. That's the top-down approach to design. It's the approach I tend to take when I am designing a database. But there is a second approach, which we'll be talking about this week, called normalization, which is a bottom-up approach. And I'm going to skip ahead a couple slides to this one. And I know it's got a lot of text on it, but the general idea is that you can either use a top-down approach to design to get a set of well-designed relations, or you can use normalization as a bottom-up approach. And if you use ER modeling as a top-down approach, you often use normalization as a validation technique to check the structure of your relations, because it's easy after you've drawn the ER diagram to have some redundancies that can be eliminated by normalization. I'll show that probably toward the end of the lecture today. Also, I'd said this with ER design, but I want to reiterate it. In this course, you get design documents or requirements documents presented to you via a homework problem or a midterm problem. But in the real world, you're going to have to generate that requirements document, that document that describes the problem. And the way you do that is you go to your data sources. So there are different sources for that. You have your users that you can talk to, and they will give you requirements or information about the way a company operates. Another good source of information is forms or reports. Often the information that is recorded on a form or a report is going to end up somewhere in your database, and the reports may end up as views. And then you also may have things written down. They may have a pre-existing data dictionary or data model that you can work from if you are revamping the database. And they probably already have some data model, or if they have some file system, they have a pre-existing data model that you can work from. So these are all data sources that you can use and integrate to come up with a requirements document. Okay, so backing up, there were some materials to have handy, but so normalization seeks to decompose relations into groupings of logically related attributes based on something called functional dependencies between the attributes. Now, that really isn't necessarily a relationship. When I first started, I thought that a relationship and a functional dependency were synonyms, but they're really not. They're really two different animals. And as we go through, you may see that better. Basically, well, let's actually continue. So you're basically trying to decompose relations into groupings of logically related attributes. And you want to minimize the likelihood of introducing redundancy and inconsistent data in your database. Now, redundancy has two problems. First of all, it takes extra storage. Secondly, it leads to inconsistency because when you update one piece of redundant information, you have to update all the other similar pieces of redundant information. So normalization is seeking to minimize inconsistent data and minimize redundancy. Okay. So to take a look at how you could end up with redundancy, we're going to look at a badly formed relation, but one that you could easily come up with from a requirements document. So perhaps you decide that I'm going to basically I'm going to represent the staff as a directory. So you just decide that's the best way to do it. So each staff person is going to have their name, their position, their salary, the branch number they're at, and their branch address. So that's kind of looking like a directory, like a telephone book. Perfectly reasonable, but it's got redundant information in it. Where do you see redundancy here? Pardon? I heard several things, so.
Staff name and branch address.
Okay, so is the staff name actually repeated? Not here. It could get repeated, although I'll argue in a moment that's not quite. The branch address is definitely redundant. You have 163 Main Street repeated multiple times. You have 22 Deer Road repeated multiple times. And in fact, you can see that if I change the branch number from B5 to B6, or actually no, let's say I move B5 to a new address, I'm going to have to make sure that I update all of the addresses in this relation, or else there'll be some inconsistency. Okay? Now, there are some other redundancies here that actually aren't redundant pieces of information. So you see the same salary, 9,000 and 9,000 here. That's not necessarily, it could be, but it's not necessarily a redundancy. And that is because it just may so happen that Mary Howell and Julie Lee make the same salary, but one might get a raise and then it would no longer be a redundancy. They're actually really two distinct pieces of information. The same would actually apply to a name. If there was a second Ann Beach in the staff and they were two different people, that's not a redundant piece of information. If the first Ann Beach changed her name, we wouldn't change the second Ann Beach's name. Okay, so that's really not a redundancy. But the branch address here really is a redundancy. Okay. Now, the branch number also appears multiple times, but again, it's not really a redundancy because if I change John White's branch number to be I move John White to branch 3, I'm not moving Julie Lee also to branch 3 necessarily. So again, I don't have to go in and update everyone's branch from branch 5 to branch 3 in that case. It's just one person changing. So we really wouldn't consider branch number to be a redundancy either. It's just branch address here that's considered redundant. Okay, is that clear that not all so-called redundant information is really redundant? Okay. So there are all other, this is what is called an update anomaly with the branch address. If I move the branch to a new address, I'm going to have to make sure I update all occurrences of that branch address or I have an anomaly. So that's an update anomaly. But there are two other kinds of anomalies we worry about, insertion and deletion anomalies. Let's say that pretty much the primary key here is what? Given that it's a staff directory, the primary key is staff number. So let's say that I want to add a new branch, but that branch should not yet have any staff members. Let's say, for example, we're building the branch, constructing it. We want to put the branch in the relation, but it has no staff members. Well, if we do that, we can insert it, but we'll have to put no values for all this staff stuff. No, 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 no. Branch number might be B010 and it might have an address. But what's the problem? What's getting violated here if I make this insertion like that? The primary key can't be null. I have what's called entity integrity violation here. That's an entity integrity violation. The primary key is null. So I actually can't insert a branch into this relation unless it has a staff person associated with it. And similarly, what kind of problem could happen with deletion? What happens if I delete Mary Howell from this relation? The branch goes away. And maybe we don't want that. Maybe it's just under renovation. So the delete anomaly here is that if we delete all tuples relating to a branch, we also lose information about that branch. That's called a deletion anomaly. And in fact, every insert anomaly has a corresponding delete anomaly. So in this case, we can't insert a branch without having a staff member. And conversely, if we delete all staff members at a branch, we lose information about a branch. So every time you have an insert anomaly, you have a corresponding delete anomaly. Okay, and these insert and delete anomalies typically occur. Well, let's move on for a moment. So we have update, delete, and insertion anomalies. So three types: insert, delete, modification. Modification are actually called, well, I guess I was referring to it as an update anomaly, but now I'm using update anomaly to refer to three types of anomalies: insert, delete, and modification. Insert and delete come about basically when a relation stores information about more than two entities. I'll say critical info about two or more entities. When that happens, you're getting insert and delete problems because typically your primary key will be for one of the entities, and then all of the remaining entities, their existence becomes dependent on that first entity, and you'll get insert and deletion anomalies on the remaining entities. And typically, you'll be also storing redundant information about those extra entities, and so actually you'll end up with a modification problem as well, because in general, if your relation stores critical information about two or more entities, then the entities that are not the primary key, they will have their critical information repeated multiple times. Okay. Critical information is things other than a foreign key. So when I had that branch staff relation, the branch number is a foreign key. That's fine. That's not so-called critical information. But the branch address is critical information. It's information inherent to a branch. Now looking to share. Looking to clear the ink. Okay, so we're looking to avoid these three types of problems. And I just told you that the problems typically come about when a relation is storing information about two or more entities. So what we're really looking to do with normalization is split relations so that each relation contains information about one and only one entity. That's essentially what normalization is about, is splitting relations. So here I'll have normalization, and it's the loss. There's two properties we're trying to maintain, but what we're really trying to do, okay, what normalization is really about is ensuring that each relation contains info for only one entity. Now, the relation may not be an entity itself. It could be a relationship. It could represent a multi-valued attribute. So it doesn't actually have to be an entity, but we're trying to make sure that the relation contains info for only one entity, or I guess I should say one relationship. The same problem could come up if you tried to have a relation contain information for more than one relationship. So you're trying to make sure each relation contains info for only one entity or one relationship. And in doing that, there are two properties that we're looking to maintain. One is what is called a lossless join property. So if we break a relation like the staff branch relation in two, or break it into two relations, we want to be able to join them back together without any loss of information. And that's called the lossless join property. So we can reconstruct the original, any tuple in the original relation, we can reconstruct by joining the relations that we have decomposed the original relation into. That's the lossless join. There's no loss of information. And the second property we want to preserve is our functional dependencies. We haven't yet told you what a functional dependency is, but roughly speaking, it's a constraint of some type. And if we have a constraint on the data, when we break the relation into two or more parts, we want to make sure that we don't lose that constraint. The constraint still applies. In that case, generally the constraint is moved to one of the smaller relations. It's still present, it's just generally in one of the smaller relations. And the book talks about it as a constraint. Roughly speaking, a constraint is going to be synonymous with something that we call a functional dependency. You're thinking, okay, Brad keeps talking about a functional dependency. I wish he would be telling us what a functional dependency is. Well, your wish is my command. There it is. This is a functional dependency is a relationship among attributes. So remember I said that when I first started doing databases, and this was many years ago, but initially I thought, well, what's the difference between a functional dependency in normalization and a relationship in the ER model? Well, in the ER model, what is the relationship among? What is it among attributes? Among entities. So that's the critical distinction. In the ER model, a relationship is among entities. In normalization, a functional dependency is a relationship among attributes. So it's more bottom up. The ER diagram is taking the big picture, looking at the macro relationship between entities. Normalization is taking the micro view. It's looking at the relationship among attributes. So bottom up rather than top down. Okay, so functional dependencies describe relationships among attributes. And the way we write those relationships is with an arrow. So on the left side of the arrow are the attributes that are determining the value of the attributes on the right-hand side. This is really a function. Even though in relational databases we're writing it with an arrow, what it's really saying is f of A equals B. So it's really A is the independent variable and B is the dependent variable. So that's another way of thinking of it. The independent variables go on the left side of the arrow and the dependent variables go on the right side. But it's a function in effect. Okay, and as we learned in 311 with functions, each independent variable has exactly one value it maps to. The function maps each independent value in A to a unique value in B. However, you might have multiple, it doesn't say that that you can't map multiple values of A to some value in B. What it means is you can't have this situation. You can't have you can't have an individual occurrence in A map to multiple values in B. Each individual occurrence in A maps to exactly one value in B. Okay, if that's confusing, let's go from it being mathematical to it being more concrete. So let's replace A and B with position and staff name. So in that case, each person can have exactly one position, but that doesn't mean that that position is uniquely occupied by one person in the organization. We might have multiple accountants. We have multiple professors at this university. We have multiple deans at this university. So the positions might be dean, professor, student, provost. Now, provost is presumably one where only one person has it. But the point is we can have multiple people mapped to the same position, but for each person, they have exactly one position. So is that clear? No, I'm belaboring it, but it's pretty important. No, we're not sharing. Okay, so that's what I just spent a lot of time belaboring, that a position like a manager may have multiple staff, but each staff member has exactly one position. And just to make things more confusing, rather than referring to the left-hand side variable as an independent variable like you do in calculus, we're going to refer to the left-hand side attributes as a determinant, which is also different from how else do you think of a determinant as? What other math course did you take that talked about determinants? Matrix algebra. But it's not that kind of determinant. So it is the determinant of a functional dependency is the group of attributes on the left side of the arrow. It is the independent variables. And they exist for all time. So what that means is sometimes if you look at sample data, you'll be misled into thinking that there's a functional dependency where one doesn't exist. So if you just look at this directory, you may well think, wow, names are unique, so you might well think that a name uniquely determines a staff number. But that's a fallacy that you get by simply looking at this sample data. Okay, we know that in the real world that multiple people sometimes have the same name. I think there's actually even another Bradley Vanderzanden out there in this world, which surprised me. Okay, now once we got down to middle names, that finally disambiguated it. But the point is, there are generally in this world multiple people with the same name. Some names are duplicated, even when you have a first and last name. So while it may look at first blush like you could have a functional dependency that staff name determines staff number. So it may look like this is a functional dependency, that staff name determines staff number. In fact, that is wrong because that won't hold for all time. That holds in our sample data, but it won't hold for all time. We may well hire another Ann Beach or another John White. Whereas it is true that staff number is an artificial key. We do, in fact, assign unique staff numbers to each person, and therefore the first dependency you see here is a functional dependency. That is one that holds for all time. The staff number will always uniquely determine a staff name. But the converse is not true. So the point is, it helps to look at sample data, but don't just look at sample data alone. It's not sufficient. It's necessary. Remember necessary and sufficient? Necessary to look at your example data, but it's not sufficient. Okay? You need to think about, could there be other example data that contradicts what I see here? Okay? Now, your functional dependencies darn well have to cover anything that really exists in this table. That's the necessary part. So staff number really is unique. You really does uniquely determine a name. I seen some, what's Dr. van der Zanden talking about, so can you articulate it? I'm seeing you making faces, so.
So,
Yes, very good. So you may make the assertion that every primary key is a determinant. Yes. And you can go further than that. You can, generally it will, okay, I'm going to say, I don't want to be trapped into generally, every determinant is going to end up as a candidate key. That's what I was striving for. Generally, every determinant is going to be either a primary or a candidate key ultimately. Okay? So that is a good generalization, that every determinant will probably end up as either a primary or a candidate key. Now, there may be some exceptions to that rule, and I think so. For example, here's an exception to the rule where it doesn't always apply. Well, actually it might. So we might decide that position will determine salary. That is, we're not going to, managers will always make 30,000. Assistants will always make 9,000. And I was going to say, well, that may be a case where we keep the redundant data, but that may well be the case that because of that, we'll move that information off to a separate relation. So actually, even that was wrong. So we'll stick with my generalization. Generally, a determinant will probably be a primary or candidate key. So that's a good insight. Got that in your notes? Because that will help with the homework. Okay. So, next thing, characteristics of functional dependencies. So this leads into that point. Remember, a candidate key was a minimal set of attributes that uniquely determined a tuple. If you had, let's say you had a set B. That's not nice. That's PowerPoint not working with these things. So let's say you have a set of attributes A that determine a set of attributes B. And let's say further that you have a set of attributes A that are a proper subset of A, and that A apostrophe also determines B. This is a functional dependency, what we call a full functional dependency. This is what we call a partial functional dependency. And the reason we say partial is because some of the attributes in A could be deleted, and B would still be uniquely determined by the remaining attributes. So in fact, B is really only partially dependent on the attributes in A, because I could remove some subset of them, thus obtaining A prime, and B is fully dependent on the attributes in A prime. So what we're trying to get to is full functional dependencies. We do not want to represent partial functional dependencies. When we list, like in homework assignments or exams, when we list dependencies, we only want to list full functional dependencies. Okay? Just like candidate keys. Candidate keys were minimal sets of attributes that uniquely determine a tuple. They don't include extraneous attributes. Same thing with our determinants. We don't want to have extraneous attributes in our determinants. So what we want are full functional dependencies. We want our determinants to be the minimal set of dependencies that uniquely determine the attributes in B. Okay, so here's an example of a partial dependency. It is in fact true that the staff number and the staff name uniquely determine a person's branch number. That is true. However, the staff number by itself uniquely determines the branch number. Therefore, the full functional dependency is staff number determines branch number. The staff name here is extraneous. So that's an example of a partial dependency. Okay, so a quick review. This slide is a review. So functional dependencies means there's a one-to-one relationship between the left-hand side and the right-hand side. Given a value, a specific concrete value for the left-hand side, it maps to exactly one value on the right-hand side. The relationship holds for all time, not just in the sample data or in the data that may be in the database currently. It might just be that currently in the database for the University of Tennessee that all professors' names are unique. I really doubt that, but it's possible. That doesn't mean it will hold for all time. So that's what it means, holds for all time. It may be that currently in your database there appears like there's a full functional dependency like name determines staff number that really doesn't hold for all time. It could change if we added a new person. And finally, the determinant has a minimal number of necessary attributes. If you removed any further attributes from the determinant, it would no longer uniquely determine the right-hand side value. Now, in addition, a type of functional dependency that is a transitive dependency. And you've seen these in 311 or hopefully somewhere. So if you have A determines B and B determines C, then A determines C. That's a transitive dependency. Okay, I didn't actually write it here, but it's basically if A determines B and B determines C, then A determines C. That's a transitive dependency. Okay? It is this transitive dependency, it is exactly this type of dependency that is messing up the staff-branch relationship. Okay? And in general, it is this relation, is a transitive dependency is what messes up relations that have multiple entities. Because basically what you have is A determines entity 2. So we'll have, this is entity 1. Determines entity 2, which determines entity 2's info. So that's a transitive relationship. In this case, it was staff number determines branch number, and then branch number really determines everything else, the branch address. Okay, so it is transitive dependencies that lead to all the difficulties with redundant information in relations that have two or more entities. Because you get that transitive dependency. Entity 1, in effect, depends, and this is really the foreign key. Entity 1 determines the foreign key for entity 2. Then that foreign key uniquely determines all of entity 2's information. Luke.
By entity, do you mean relation or like attribute?
No, by entity, I mean one of those like branch, staff, one of those things that has a physical existence. One of those things from the ER model. That's what I mean. Okay. So transitive dependencies are bad. Again, pretty obvious what happens is a transitive dependency, that determinant is going to move off into a different relation along with its information. Okay, so I just went through that. So when you're given a requirement stock, which you will be given in this course, you will then need to determine what are the functional dependencies. So I might give you that all the basic assumptions you see in the staff branch data, plus I'll assume that the position and the branch determine a member of staff salary, just for fun. So given that information, we know that a staff number pretty much determines all the attributes for a person plus their branch number. The branch number pretty much determines the branch information. Now, this you would have to verify, but generally street addresses are unique. So generally speaking, an address is going to uniquely determine a branch number. So that's, you'd need to verify that, but in general, you can be pretty confident that a address, as long as it includes a city and postal code, probably uniquely identifies a branch number. And then I said a branch number and a position determine a salary. And since a branch address uniquely determines a branch number, we also know that a branch address and a position uniquely determine a salary. So you would want to list these as the 5 functional dependencies for the staff branch relation. Okay, so moving on, that's identifying them, and we'll have more practice with that on Thursday when we consider a case study. So just as you do with ER relationships, when you start the normalization process, it's going to be a procedure. So you first are going to identify these functional dependencies. In fact, what you normally do is you create one massive relation, which we often call the universal relation. So usually we start the normalization process by creating an enormous universal, create one enormous relation called the universal relation because it's the only relation. And then what we want to do is decompose it into a set of smaller relations. So in order to do that, we next identify functional dependencies. So the universal relation has taken care of finding all of our attributes. And buried in that universal relation is our entities. And we'll be using the functional dependencies to extract the entities and relationships, the broader relationships, the ER relationships. And we'll do that via functional dependencies. The next step is that we're going to identify the primary key for the universal relation. So we first identified all of our attributes and put them in one enormous relation. Then we identify the functional dependencies among the attributes. Now we identify the primary key for that relation. Okay, and from the functional dependencies, we may have several candidate keys, in which case we select one of them to be the primary key. Okay, so for the primary key for the staff branch relation is the staff number. And then we're making sure that all attributes that are not part of the candidate key are functionally dependent on the key. That's exactly what we said was the candidate key. So the attributes in the candidate key, they uniquely determine all the remaining attributes in the tuple. So nothing really new on this slide. This is just reiterating information you already know. Okay? So as I've already kind of started to now talk about this process of normalization. It's a formal algorithm, and I just showed you the first three steps. You get the universal relation, you identify your functional dependencies, you identify the primary key, and then you'll start step 4, which is the decomposition process. So step 4 is going to be the decomposition process. And as we proceed, as we do our decompositions, the relations will become progressively more restricted. And you'll see in what sense they become more restricted. And they'll become less vulnerable to update anomalies. Okay, to give you a quick preview, well, here's the quick preview. So researchers have gone crazy and identified a whole bunch of normal forms. The most useful are first, second, third, and Boyce-Codd normal forms. We will only deal with first, second, and third normal form in this class. We won't deal with Boyce-Codd normal form. In fact, as you get to some of the higher normal forms, you get to the same issue you had with chasm traps, which is you solve one problem and introduce another problem. But that is not true through third normal form. Through third normal form, everything you're doing is an improvement and you're solving a prior problem. And you will find that first normal form is roughly the universal relation. Second normal form is when we have managed to put all of our determinants that involve primary keys into separate relations. And third normal form is when we have removed transitive dependencies. So second normal form or third normal form, we've gotten basically separated all of, in third normal form, we've essentially separated all of our entities from the entity relationship model into separate relations. And we won't worry about the higher normal forms in this course. So you'll only be responsible up through third normal form. So unnormalized form, there is actually an unnormalized form, and that is simply a table containing either multi-valued attributes. So you might have, for example, a entry for branches, and branches might have phone number, and you might have B003, and you might have 3 phone numbers. Well, that's called unnormalized form because it violates the 1 value per cell requirement of the relational model. So basically, the first normal form is going to say basic adherence to the relational model. 1 value per cell is going to be first normal form. Another example of an unnormalized table is given in the book where they have our renters. So in effect, they have like renter number and then like the property number they stayed at, the start date. I'll just do that. And then for each renter, they might have renter number R003, and they might have, they stayed at property P01, P005 with a start date of blah, blah. So there they had what the book calls a repeating group. This isn't really, so the second example isn't really multi-valued attributes so much as it's repeating groups. So the renter 3, in one row, we have information about all the properties they have rented from us, but it's more of a repeating group. And it should be pretty obvious that the way we make this into first normal form is, how would we convert this second table to first normal form? It's pretty easy. Put the rental number separately on each line. So for each group, separate it into its own row and then duplicate the renter number. So it's pretty easy with repeating groups or multi-valued attributes. You just give each of them their own row. So going from unnormalized to first normal form is pretty easy. And then to go from, well, it does if you have a multi-valued attribute, you put that multi-valued attribute into a separate relation. That gets you first normal form. Then second normal form, the idea is that you remove all partial dependencies on the primary key. So in the staff branch relation, you actually have no, let's see, let's just, okay, to go from first normal form to second normal form, identify the primary key. Then identify the functional dependencies, and if partial dependencies exist on the primary key, you remove them. Now, if the primary key is a single attribute, it turns out you can't have a partial dependency. You can only end up with this situation if your primary key consists of multiple attributes. So I think I will actually end things here because I'm going to have to talk about it more. So make sure that before you take the quiz today, you just know what the definition is for first, second, and third normal form. I told you informally what they were, okay? But just review that. First to second normal form means we're going to remove what are called partial dependencies. Second to third normal form, we're going to remove transitive dependencies, okay? I will show you how we do that on Thursday, and also on Thursday I'm going to do a case study. So before you come to class on Thursday, try to read the hotel case study that you see for 928. Okay, and I will see y'all on Thursday.